In this video, I would like us to discuss the relation between series and differential equations. So specifically, I want us to look at a question from homework 11.9, number 8 on WebAssign. This question asks first to show that the function given by the series sum from n equals 0 to infinity, x to the n divided by n factorial, is a solution of the differential equation f prime of x equals f of x. So how would we verify this statement? Well, consider this power series for f of x. It is easy to verify that it has infinite radius of convergence. In fact, that is something that we have done in the course of section 11.10. This series converges for all values of x. In particular, it can be differentiated term by term. Let us go ahead and differentiate both sides with respect to x. On the left, we're going to have f prime of x. On the right, we will want to differentiate the infinite power series, which, according to a theorem that we have on differentiation of power series, just means that we have to differentiate every term in here separately. Now, how do we do that? Well, the nth term here is a constant multiplied by x to the n. So we will still have n factorial in the denominator. In the numerator, we differentiate x to the n, which gives n times x to the n minus 1. Observe that for n equal to 0, the 0th term vanishes. We'll have 0 times a power of x. So this infinite sum is exactly the same as the sum n from 1 to infinity, n times x to the n minus 1 divided by n factorial. Okay. So here, at this step, I would like us to recall that n factorial is n minus 1 factorial times n. This will allow us to perform cancellation in this fraction. So we are looking at the sum from 1 to infinity, n times x to the n minus 1 divided by n times n minus 1 factorial. Great. So here is our cancellation. The resulting series is n from 1 to infinity, x to the n minus 1 over n minus 1 factorial. Now, in order to show that this series, which gives the expansion of f prime of x, is the same as the series for f of x, because that is our goal. So our goal is to show that f prime is equal to f of x, and the way we'll do it, we will show that the series we obtained for f prime of x coincides with the series that we had for f of x in the first place. So to do that, we will need to change indexing. So as you can see, the difference between this series here and the one we had for f of x is that the indexing starts at 1 and not at 0, and we have n minus 1 everywhere in place of n. So the way to proceed is to say, let us introduce a new variable which is equal to n minus 1 in this series. Then we have f prime of x equals the sum k equals 0 to infinity. When n is 1, k is 1 minus 1, that is 0, and it goes all the way up to infinity. X to the k divided by k factorial. And here we go. This expression is exactly the series we had for f of x with k in place of n. So of course it doesn't matter what you call your index of summation, therefore this series is exactly what we had for f of x, and f prime is equal to f of x. So we have just shown that the function given by this power series satisfies the desired equality. The second part of this question on WebAssign asks to show that f of x is in fact e to the x. There are two ways to do it. So first option is to use Maclaurin series as is done in section 1110. So in section 1110 we show that indeed the Maclaurin series of e to the x is precisely given by this series here. Another way is to use the differential equation. So we have just verified that f prime of x is equal to x, where, remember, the function f of x is given by the power series. Since we have this differential equation for f of x, we know two things about f of x. So from the second approach, we can proceed as follows. For f of x, we know two things. F of x satisfies f prime of x equals f of x. That is something we just showed. And secondly, in addition to a differential equation, we need an initial condition. So let us evaluate f at 0. So when x is 0 in this series, every term that contains a factor of x will vanish, except for the 0th term. The 0th term, when n equals to 0, contains no factors of x. So it would be, for n equals 0, we have the 0th term here, and evaluated at x equals 0, it gives 0 to the 0th power divided by 0 factorial. Now, here, this is not really an indeterminate form. So we're just agreeing to say that 0 to the 0th power is 1. So this is not an indeterminate form, this is just a convention that we will follow. Now, we have another convention for 0 factorial. We said that 0 factorial is said to be 1 as well. And so, as a result, we see that f of 0 is 1. So we have an initial condition. Now let's go ahead and solve this differential equation with this initial condition and verify that e to the x is indeed a solution. So we have dy over dx equals y of x. You can see that this is a separable differential equation. So we can separate variables to produce dy over y equals 2dx. Then let's go ahead and integrate both sides, which gives log of absolute value of y equals x plus a constant. So from this point, it's the usual procedure we will follow for solving differential equations. Let us raise e to the both sides of this equality, which gives absolute value y is equal to e to the c times e to the x. Let e to the c be a new constant, and we have y equals plus minus this new constant times e to the x with k positive. As usual, we merge the plus minus cases into the possibility of k being negative, which gives y equals k e to the x with k not 0. And finally, we verify that y identically equals to 0 also satisfies this differential equation. When y is identically 0, we have dy over dx equals 0 on the right hand side. Great. So the differential equation has, the solution of the differential equation has this form, plus initial condition gives that y at 0 must be 1, as we observed previously, and we conclude that since y of 0 must be 1, we must have k times e to the 0 equals 1, which gives that k equals 1 as well. And the conclusion is that the solution of this differential equation with this initial condition is indeed e to the x. It is the unique solution which satisfies our initial condition. And so we have successfully used the second method, according to which the differential equation f prime equals f of x plus the initial condition implies that the function we are dealing with is in fact e to the x. Another verification of this fact is contained in section 1110 and uses the Maclaurin series.